We start talking about the infrastructure and the platform, and now we will start talking about the pilots to validate the technology. The first one has been developed in Italy, in the region of Olbia, and it's about an IP monitoring tool to support the grid automation. Before to start, let me give you some numbers about the size of the grid in the area of Sardinia, in the region. So we had more than 100 primary substations, so station to transform from high voltage to medium, together with medium voltage switching stations. It's quite a single thing that we have in Italy. More than 900 medium voltage feeders, and the majority of them are automated. We have a total of 16,000, almost 17,000 customers, a substation from medium voltage to low voltage. So the majority of them, it's only remotely controlled, and a minor part is in automation. So as we were exploring in the opening side, to have remote control and automation, we need a reliable digital layer. Inside those secondary substations, we have 7,000 fault detectors. And at the end, we are serving a lot of customers with almost 39,000 kilometers of power lines. So those numbers are impressive, and there is a regional control room in the main city down in the south of Sardinia, from which the operators are controlling the region, the grid of the region, in a 24/7 shifting. And this picture is during a storm. You see the clouds up in the map that was arriving in the region. So they have a lot of information to handle, and without a reliable automation system, it will be impossible to control and monitor a grid by only like few people in the room. So to do this, E-Distribuzione developed an automation tool. It's called Smart Fault Selection. It's already operating with optical fiber and some areas with 4G LTE. Just to give you a quick example on how it works, let's imagine in the schema. I think I know that it's small, but let's. I don't know if there is no laser pointer. Okay, in the two power lines, the red and the green, there are a set of secondary substations, and for example, there is a fault inside the grid. So all the smart fault detector are feeling that there is a fault in the grid. They are going in a lock. So all of them says, okay, I saw that there was some fault and I'm waiting. They start whispering to each other and saying, did you see a fault? Blah, blah, blah. I saw it, yeah. At the end, they are able to even identify which switchgear was the last one seeing the fault. That switchgear is opening automatically without affecting all the customer before the fault. And also opening the other side after the fault and feeding back from the other side. All this operation is called Smart Fault Selection with self-healing. It's performed in less than 1 second. So the speed and the reliability of the digital message has to be extreme. So that's why we need a tool to monitor the IP network to ensure that these performances are always ensured. There is a dedicated team in the region, but in each region we have a similar team that are controlling the status of the telecommunication infrastructure. Of course, there is not only the mobile network, but this is a 5G project, so we are implementing something in 5G. And these are the IP requirements. So we need a high reliability, a total end-to-end latency, so from each device to communicate to each other below 40 milliseconds. Packet loss, it's almost 0%. The jitter is the delay, it's below 5 milliseconds. And the latency in the radio part below 25 milliseconds. These are a series of data that we set as an expectation when we started the pilot. Going back to the schema I presented in the opening, we have the control room system, the core network, the radio part, and our field devices. So, to ensure that at least the radio part is operating, we implemented a network application inside the core or next to the radio access network to monitor the connection between the core side and the field devices. This is a unique tool because whatever happens now, my colleagues in the control room are not able to communicate with the field device, and it's 1-0. It's working, not working, but nothing about the quality, if there is any change or degradation in the quality of service. So we are splitting the path more or less in two, and we are monitoring the radio part. So whenever there is a problem, they are able to check from inside the infrastructure and check at least if that part is working. That means that they don't need to send somebody in the field, because usually what happens, the device is not working, let's send somebody to try a reset, change the equipment, change the batteries, and so on. So if we can check from the radio part that the device is working, maybe something here. So while opening the ticket to the telco operator, says, okay, the final part is working, no worry, just let's analyze the first part of the path. Or vice versa, maybe there is a degradation, no need to worry about whatever is behind. Let me add some names. So the control room system are operated by a distribuzione as the field devices. In the middle, we are using the Win3 infrastructure, and the network application has been developed by STAM. The application is working in a Mac server provided by HPE, and we were not describing the orchestration part. I think we will have time to talk about this aspect. So the orchestration and the network application controller is provided by nearby computing, and we designed together with my colleague from Grid Expertise all this implementation. So what are the features of this network application? So as I mentioned, we are able to monitor constantly the communication parameter. We are monitoring specifically the last segment, so saving some effort in avoiding intervention of physical people on field. We can check the degradation of the medium, because, for example, it happened in the past that the parameter were going slowly through a degradation phase, and we can identify those kind of slow degradation and make the correction before it's too late. And then the network application is also able to send alarms to the technical team to start checking what's going on. How things are done today without the network application, we only have the working, not working information, and usually there is a ticketing system to the telco operator. Let's not mention that in NL Group we have our core, so the radio part is demanded to different telco operators. So the identification of problems is even more complex. So this is just a frame of the network application that it's allowing to filter the information, aggregate, and etc. I'm not entering in detail. It's more relevant to understand the logic and how it's working. And these are the pilot sites. So in each secondary substation, we implemented high-speed circuit breakers, a series of digital fault detectors, and a router that it's able to utilize the 5G with a dual APN. So these are the three main devices that are implemented on field. To demonstrate that the connectivity it's working properly, we made a real test of automation. So now the picture is not the best ever, but we were connecting the grid through a resistor directly to the ground to simulate a fault. And then the automation system, as we saw in the slide, identified that the fault was exactly in that point, and the grid was automatically reconfiguring itself to isolate this faulty part. So the test on field has been successfully executed. This is the team. And these are the parameters during the execution of the test. I understand that the duration of the sample is quite short, because it was like 3 hours around the execution of the test. But we see that all the parameters are within the given expected value. We are still performing the analysis on the long term, and for those who are curious, the deliverable will be publicly accessible, and all the analysis will be made in that document. So at the end, the use case and the pilot was successful. So all the KPIs were in line with the expectation. The smartphone selection was performing according to the expectation, and a special mention to the network application, because we were not only using it during the execution of the test, but during the implementation of all the field devices to check, is the antenna positioned correctly, blah, 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 why the communication is not working, let's check the configuration of the firewall, and a series of steps that usually are performed while implementing remote control and automation on field. And the operative team has been supporting in the day-by-day operation by this network application. So the feedback from them has been really positive. So that's all from my side. Thank you. And let me call my colleague Ana Romero Garcia from Edistribución, who is the leader of the Spanish pilot. Thank you.
Thank you, Daniele. Can I have you?
Yes, that's yours.
Okay, good morning, everyone. As Daniele said, I'm the coordinator of the demo, the Spanish demo. I work for Edistribución. I've been involved in the demo since almost the beginning. And I'm so excited to be here sharing the results of the work done during this demo. So, sharing a bit of Edistribución infrastructure, our main role has been to provide the architecture for our infrastructure for testing purposes. We have also involved our experts from telecommunication department, health and safety department, and the grid operator. They have been very involved, and we have also shared our requirements for the industry to transition towards smart grids. So let's see the numbers of the infrastructure. We have more than 300 kilometers of power line in the Spanish region. More than 1,000 primary substation and 130,000 secondary substation. Definitely a critical infrastructure that requires a careful maintenance. So it is on this maintenance activity where the demo is focused. Because safety is the priority for the DSO, we have the 5 golden rules. These rules are 5 steps that ensure that the electric elements are de-energized and the workers are working on a de-energized area and the work zone is safe, okay? If we have a look to the 5th rule, it says that the working area must be bordered and signalized. Also, we have the stop work policy that says that all works must stop when any situation may endanger the safety of individuals or the environment. So, how a Smart5Grid project add value to the DSO? You must be wondering. Okay, by the automatization of the delimitation of the working areas, it is a reinforcement, okay, of the current safety measures. It is done by virtually building a volumetric cube where the workers must remain during performing these maintenance activities. The workers and the non-isolated tool, this is very important. We have a real-time monitoring of these workers for them to remain inside this area. Whenever they will go close to the border of the zone, an alarm will be triggered to warn of the danger. So let's see a video of how this works. This is the substation, Eco Garraf substation. It's near Barcelona, inside the Garraf Natural Park. It is a 66 kilovolts substation where we deploy our devices. And I will show you how the network application works. These are the workers that are going to perform a maintenance activity. So here is how they physically border the work area with these plastic fences. And here we can see this virtual cube built by the NetApp that triggers the alarm whenever they trespass the working zone. So this innovative tool can also be possible thanks to three key elements. Sorry, that was me. First of all, a private 5G network with dedicated resources that enables the real-time monitoring. It also ensures to be secure and isolated because of a dedicated slice. On the second place, we have a series of cameras and portable sensors. They are wears tag that the workers are wearing on their wears that locate their position and send through the 5G network to the network application, which is the third key element in the solution. And this network application aggregates the information coming from the field sensors and compare it with the work area that have been previously defined in the dashboard. It will trigger the alarm when it decides, it sees that the worker or the tool is close to trespass the zone. Okay. So let's see the architecture of the use case. Here we have on the left the field sensors, cameras and sensor connected to the CPA. Also we have the alarm beacon. We saw it on the video. The information is sent through the 5G network using the band frequency N77 from the Spanish Ministry. In Spain, there is no spectrum for public networks, private 5G networks, sorry. So we are using this with investigation purposes. So the information will arrive to the 5G equipment, the 5G antenna, remote radio unit, and here we have the servers installed in the substation. These servers are connected through the Endesa's VPN to the, in first place, the Neutron platform that manages the 5G network, and to the Neutron platform, which manages the 5G network, and to the Smart5Grid platform, where the network applications are deployed and where we download images and network and NetApp controller manage the applications. So, seeing in a more detail the private 5G network, it is composed by the CPE. We set the customer premises equipment, and we have the part radio composed by the antenna, remote radio unit, and VRAM. VRAM is based on Amarisoft. The second server, which is network application server, there we have a Kubernetes cluster deployed, where the network application is running. And finally, we have the core, the 5G core server, which is the main server for having a 5G network, and connects the end devices with the network application. Some software capabilities are, for example, that we have Kubernetes cluster managed by Helm. And here are some hardware capabilities that are basic from the network application server. One limitation is that we are not supporting GPU. Instead, we have this CPU. Okay. So let's move again to the demo site. As I said, it's near Barcelona, 66 kilovolts substation, which main objective is to elevate the voltage from a biogas generation plant that is nearby. Let's see the field devices. We have in this photo on the left cameras and sensor. In total, we deploy 6 cameras and 10 sensors to monitor the park of the substation, equipped with artificial intelligence in CADAS microprocessors. And this is the model of the cameras in RealSense, the 400 series. And on this photo, we have the CPE that sends the information through the 5G network. The 5G antenna, which is on this upper photo on the right corner, it's installed on the outside of the technical house of the substation. Inside the technical house, we have the servers that we have been seen before. And this is, we have already seen, the demo zone and the alarm beacon. Okay, so how is the delimitation of the working area done? Currently, it's done manually with these plastic fences, and in the network application, the manager of the works should decide where the points of this safety area will be, and he or she will measure what the reference from the poles and insert it on the network application dashboard, which is here. Okay, only the managers of the work can make changes on these critical areas. So only the people with administrator roles can insert or delete working areas. Once a working area is defined, we can name it and save it to have it predefined. More than one safety area can be activated at the time. As commented, as soon as one safety or working area is activated, whenever someone or something goes near to the border, will trigger the alarm. Okay, we perform several tests with the field devices, the network application deployed on the substation, the 5G network working correctly, services up and running, and we obtain these performance indicators. Starting by the latency, the information that arrives to the NetApp is whether the worker is in danger or not. So we must be really fast so the network application can compute the position as soon as possible. We obtain a value of 14.5 milliseconds, which is clearly under the expected value, the target value, which was 50 milliseconds. So we are happy. And regarding the jitter, which is the standard deviation of the latency, it should be ideally half of the latency, and we see that clearly is below that value, so it shows a stable connection. Regarding the data range, we measure the uplink data range and shows 66 megabytes per second. We can note here that we only have a bandwidth of 40 megahertz. So if we have it wider, we could even have a higher value. But at the end, we meet the initial requirement. Regarding the availability, it is important for security-related use cases to have always the 5G network and the network application available. So to perform this test, we simply left the network operational during 1 week, and the result shows 100% of availability. And regarding the reliability, which indicates the rate of information that successfully arrived, or on the contrary, the number of packets lost, we left during 1 week a ping with default settings, and after that we measured that 100% of this information arrived. So again, the KPI was achieved. Okay, so as conclusions, our use case validation, we can say that monitoring devices has been deployed to monitor the people on field. Artificial intelligence can detect the people. Also, a private 5G network has been successfully deployed, and it enables the real-time monitoring. The network application has been deployed in the substation via the Smart5Grid platform, and it's running on the edge. We can also set the working areas even remotely. And the location outcoming from the field sensor is currently computed on the network network application to determine whether triggering the alarm or not. From the DSO perspective, we think that our conclusion is for implementing Escalate or any security tool, related tools, the technology should be at a high level of maturity. However, the project sets perfectly the basis to move toward digitalization, sensorization of the energy infrastructure. So, thank you.
Thank you, Anna. So we are a little bit ahead on the schedule, and we are anticipating the presentation from my colleague Ralica Rumanova from Entra Energy. Thank you.
Thank you, Daniele. Hello, everyone. Good morning. As Daniele already introduced me, I'm Ralica Rumanova from Entra Energy. Entra Energy is the use case leader of the third demonstration within Smart5Grid project. And I'm going to tell you what we do in this pilot. So just to remind you what is the challenge or the business need that we try to address with the pilot that we are doing. As Vivian has explained quite well and robust, the energy sector goes through a big transformation, moving from centralized to decentralized system. We see a lot of businesses going electrical. The production of the energy gets more dispersed geographically, relocated, and dependent on the renewable sources as the share of the energy production gets higher from renewable sources. And all this really puts a big challenge on how the energy sector can perform its operations in a stable manner, and at the same time allow for adoption for renewable sources in a higher pace. So what the pilot really acts on is the perspective from the distributed energy, renewable energy resources, and how their operation can be improved so that to allow for smarter grid. And here are some of the challenges of the sector that our use case is aiming to address. What we do is we do a remote monitoring for improved visibility and controllability over distributed renewable resources, so that they perform better and their integration is faster, more effective, and easier. We perform and have developed and demonstrate an application that works toward improved performance of the renewable energy resources for their improved operational excellence. The use case contributes to better distributed renewable resources, to integration to the grid and to the grid stability that I'm going to cover in a minute. And last but not least, it really contributes to the empowerment of the flexibility services for the smart grids in the future. And as it involves, as the project, the pilot involves players from different domains and different expertise like telcos, software developers, and energy professionals, it really does create a new knowledge, new technologies, and opens the perspective toward the new market and business models that could be implemented. So that's the pilot site. That's an actual photo of our wind turbine. So the use case uses the actual measurements from a wind turbine, that is Vestas V20 2 megawatt turbine located in Sliven region, which is in the middle of Bulgaria. Due to lack of commercial 5G coverage, we selected a set of signals coming from the SCADA system and some additionally installed IoT sensors, and we created a digital replication of these signals over an IoT device that is actually reporting the measurements and to the network application. In order to convey with the security requirements. So we use OPC client service protocol for the replication of the signals. And as I said, we collect the data from the SCADA system and the IoT sensors, which is another kind of a upgrade that we demonstrate that we can collect data from different devices, different systems. And this really makes the solution scalable. And we use MQTT broker as a communication protocol for secure and fast communication, as it was, I'm going to explain later. Okay, so that's the solution that we do. We have developed one application that has three virtual functions, three functionalities. One functionality performs real-time monitoring over the renewable energy resources, variable in type and size. The other functionality performs predictive maintenance enabler, so it acts as a predictive maintenance enabler. I'm going to explain in a minute. And the third functionality, we decided to separate it and create it as a new additional functionality, is the MQTT broker that acts not only as a way to communicate the signals from the devices in the system, the few devices in the systems, but it could act as an easy way to implement some additional sources to the current assets under management and under monitoring, as well as third-party systems like, for example, battery management systems. So it allows easy integration of different kind of distributed energy resources to the network. So it opens the way to third-party experimenters. So that's the home page of the solution that is really versatile, really cost-effective, and really multi-scalable. Because it fits and serves the needs for different in size, renewable resources, like from micro to mid and even big scale distributed energy resources could be monitored, and the data could be collected and recorded. Versatile in terms of source, renewable source. So as you see, we have functionality that monitors the wind turbine, the real hydropower plant, that is again a hydropower plant that Entra Energy operates, a solar plant. We use for this simulated data that are actual data, but they are pre-recorded. And this is the IoT device is shown here on the homepage, just to show that it easily integrates additional resources or any kind of sensors and systems that could be visualized and monitored. The network application is, and the functionality is really versatile in terms of reporting, data reporting frequency, in terms of the sources of the signal, because we can collect data from, as I said, different systems, different devices, etc. In terms of diversity of signals as well. So for the easier and better visualization, we organize the signals in different categories like technical, environmental, electrical, grid. We can easily implement some market signals like the electricity price, etc. So it's really versatile. It is location independent as it uses 5G. So whenever there is a coverage, 5G coverage, this application could work and deliver within the set requirements. And it is secure by design, as it really uses and involves protocols that are secure, provide high security. So that's the solution architecture. We have the field devices at the bottom. We decide what kind of signals we're gonna collect. We collect them over OPC protocol and over MQTT when it comes to an IoT device. A digital replication, as I said, of the signals was created, and through a 5G gateway, which is a IoT device equipped, connected to a 5G modem that is equipped with 5G SIM card. The connection is done over a private APN network to Vivacom infrastructure and to Vivacom cloud, where the net application is hosted. So the MQTT broker acts as a communication agent, and the network application, as I said, is hosted in the Vivacom cloud and is connected and verified through the different elements of the Smart5Grid platform. So it's validated and verified by the VNV module. It's registered on the OSR, and it's deployed by the NetApp controller provided from nearby computing. And of course, to show the overall solution, because it is a solution, it is a service, at the very bottom we see the customers of the application that are the distributed energy resource owners, the renewable energy asset owners, and the grid operators. Who can have access to the real data, real performance data of the asset. I'm going to cover this at the end about the KPIs, but maybe here is the moment to mention that when we set the KPIs and the field validation parameters, we've included not only parameters that are measuring the network performance, but also the parameters that are measuring the net application performance, so that we have all the elements from the bottom to the end user that are measuring the overall performance of the service. So to get into detail, this slide and the following slide are dedicated to the functionality that that provides the real-time performance monitoring over the assets. So we have different type of renewable sources that are monitored: wind, hydropower plant, and PV. We have different systems and sensors and devices that we collect this data from. So for each source, we have different systems and devices that are connected and reported. We have more than 30 signals that we read, visualized, and record into a database as historical data. These signals are organized in groups so that they make sense and for better visualization. And apart from a user being able to see the performance of the respective type of signals, the signals could be manually selected so that the user can get into more detail to see a specific parameter that is of interest. And the users, as I said, are the distributed renewable asset owners and operators, as well as the grid operators. and their respective roles. They have secure access to the application under respective roles and access. This is the other slide on the real-time performance monitoring that shows that apart from the visualization of the performance parameters, we have developed a simplified alarm functionality. This is the alarm log. Then we have the records of the raised alarm. And as I said, MQTT functionality works as a communication agent. So as soon as an alarm is raised, the MQTT sends alert back to the asset, so the operational team can act immediately on the fault detection. So this functionality aims to lower the reaction time and is a kind of a step forward to improve the operational maintenance. Because of a lot of technical and legislation reasons, we couldn't really demonstrate in real life a controlling functionality. That's why control application and functionality was demonstrated as part of the pre-pilot demonstration within a hardware in the loop demonstration performed by University of Cyprus. Within this pre-pilot demonstration, wide area control schematic was demonstrated. That coordinates the performance of distributed energy resources to support the frequency stability of the power system. So the demonstration used real-time measurements that were processed to measure and identify some imbalances. And the data exchange was done over 5G communication that allowed the deployment of the wide area control. This is the schematic of the testbed architecture that involves a digital twin of the power grids, a hardware network emulator, and a hardware controller for the overall hardware in the loop configuration. And these are the results that show the contribution of the 5G and the improved reaction time for frequency stability versus the baseline and versus state-of-the-art solutions. So, monitoring and control. That's the second functionality that the developed under use case 3 pilot has, network application has, and it's a predictive maintenance enabler. The predictive maintenance enabler acts as, firstly, it's the first must-have so that real predictive maintenance algorithms are developed, because in order to develop algorithms and to train algorithms, you need to have the data. So it collects different type of data and signals from different systems, from the wind turbine, and records it into a database. Then whoever the user is can select a particular period of time and particular signals that he wants to see as historical data. This data is visualized, so we see the trends, we can fine-tune the request, and then the signals could be exported for further analysis and use. The predictive maintenance enabler functionality has an additional, very simplified predictive algorithm that was developed by the software developer of the application software company that uses the linear regression and predicts when a certain signal will reach a certain predefined value. It's really simplified indeed, but it was developed so that to show the potential of the functionality to act as a predictive maintenance enabler, and the data to be used to train more complicated multi-factor algorithms. And these are the KPIs that were validated, that were set and then validated. As I said, both, some of them are network related and some of them are application performance related. These are the values that we measured within the very last month of operation of the pilot, so it's quite a long time. And the parameters showed, the actual results showed that the key parameters have been validated and achieved. So, in conclusion, I want to remind once again that the energy transformation really puts some challenges, and some of the biggest challenges are coming from the higher portion of electricity being produced from renewable sources. Renewable sources are getting more and more in terms of number and smaller in terms of size. They're very often managed by not professionals. We see some players like consumers going prosumers with alternated roles. So it is key for those assets to be really monitored as a first step toward improved operations. It's key for the grid operators to gain visibility on what actually going on in their grid so that they can predict further the production flows, as well as some control function, to perform some control functionalities, and in a longer term to plan upon the investments that are really needed so that the grid can sustain the integration of these renewable resources. Telecoms, technology developers and energy professionals really unite forces into finding the best solution, because it really is a multi-industry and multidisciplinary game. And as I saw on the telco presentation, the telecoms are already doing these steps forward. And at the end, I hope we're gonna speak a little bit more on the key exploitable results section. Use case 3 demonstrates a really scalable, that is needed, simple and cost-effective solution for real-time monitoring, and as a next step further forecasting and control over the distributed small to mid-size energy resources. And in that way, it really contributes to the digitalization of the sector that was really needed and was mentioned a couple of times during the presentation so far. And contributes toward improved operation both for small to mid-size renewable energy resources and the grid operations, stable and grid operations. So more information you can find on deliverable 6.3 that really detailing explains of what we've done, how we have measured, plus questions are always welcomed. Thank you.
Just stay with me 1 second. I want to comment and give all my compliments to our colleagues from the Bulgarian use case, because just to connect what we talked about in the first part of the morning about energy industry, telecommunication industry, and this pilot demonstrates that the technology is really filling the gap. In terms of scalability, if the boss of Entra Energy decides to buy a new power plant, it's just about replicating the software. So scalability, it's one click. In terms of computational power, we didn't mention the orchestration paradigm. As you can understand, this universe, it's quite big, but we were not mentioning the potential of orchestration. Orchestration is part of the virtualization frameworks that allow the code to be executed either in the edge or in a central cloud, or maybe replacing that specific edge node because maybe it's too busy. So there will be one extra node that can complete. The other step is the federation, so distributed computational power that goes in support of the lack of data centers for the evolution of the approaches to remote control and operation. So all my compliments to the team because they were also going beyond the first design, implementing the predictive maintenance and also some example on how to leverage on data to extract value. We are also cooperating in a new project that started in January, Twin AU, about digital twin that demonstrates how algorithm can cooperate with a digital replica. And this predictive maintenance enabler is an example that within a small project like Smart5Grid, we were opening up for further implementation. So data is there, and it's ready to be further exploited. So thank you all. I see that the table, everything is almost ready. So let's have a lunch. Thank you all.